Before 2023, systems like WebGPT, SayCan, and React existed as disparate implementations. They solved specific problems in search, robotics, and reasoning, but they lacked a shared taxonomy to connect them. The underlying challenge was that foundation models are isolated. They have deep semantic comprehension and vast world knowledge, but they are severed from external environments. Because they rely entirely on parametric memory, they hallucinate facts. They fail at basic arithmetic. They lack today's data, and they cannot exert physical force. APIs and external tools are the functional opposite. A calculator or a weather API is precise and connected to real-time events, but it lacks the reasoning required to direct its own execution. This is the complementarity thesis. The model provides the reasoning, and the tool provides the accuracy. By combining them, you resolve the structural weaknesses of both. A 2023 survey by Chin and colleagues organized these systems into a single taxonomy. They define the components, the mathematics, and the training streams required to turn a foundation model into a controller. Tool learning provides the mechanism needed to ground a text generator in external environments, allowing it to perform verifiable actions. To understand how this works, we have to map the architecture of the agent loop. First, the toolset uses APIs to take model outputs. Second, the environment executes those tools to generate feedback. Third, the controller acts as the cognitive engine. Finally, the perceiver formats this feedback for the controller, closing the loop. Engineers often assume that agent frameworks distribute intelligence across several nodes, but the perceiver lacks reasoning. It is simple plumbing, often just a template for concatenating feedback. The actual reasoning is contained strictly within the probabilistic outputs of the controller. This continuous data flow, from the controller out to the environment, through the perceiver and back, forms the foundational operating system of the agent. Inside that controller, the process is governed by a specific set of equations. Equation 1 defines the controller as a probability distribution over the next action. It is conditioned on the user's query, environment feedback xt, and prior actions ht. Removing feedback in history reduces this to standard autoregressive text generation. Environment feedback is the mathematical constraint that grounds the model in reality. Without this conditioning, the agent returns to being a text generator with no awareness of the tools it just invoked. We then have to ask how this grounded model calculates what specific action to take at any given step. Equation 2 factorizes the decision into two parts. First, calculating the probability of selecting a specific tool. Second, generating the correct execution arguments. This mathematical factorization directly translates into the code skeleton used to build the agent. By separating tool selection from tool execution, engineers can insert retrieval pipelines into that first step. This allows the system to scale to thousands of APIs without overwhelming the model's context. This equation defines the architectural boundary required to build and scale functional tool learning software. Once the agent can call tools, it needs to sequence those actions to solve complex prompts. Early systems used introspective planning, generating the entire plan up front. This approach is fragile. If the agent encounters an error, the pre-computed plan becomes invalid. Imagine an agent calls a weather API that throws a key error because it doesn't recognize a city name. Modern systems use extrospective planning, acting incrementally and reading feedback. By reasoning step by step, the model dynamically replans around the failure, bypassing the error with a green fallback loop. The technical advantage of this method is the capacity for execution recovery, maintaining resilience even when the environment produces unexpected results. To make the controller effective at these tasks, engineers use two different training streams. The first is cloning expert trajectories through demonstrations. This can be done with human data or by having the model bootstrap and filter its own successful API calls. The second is learning from feedback. This uses reinforcement learning to explore tool combinations that may not exist in human training data. We can test the framework by mapping existing AI systems into a matrix of these categories. The React architecture fits into the extrospective multi-step quadrant. Toolformer maps to self-supervised demonstrations. The ability to categorize these independently designed systems within this grid suggests the framework correctly identifies the structural variables common to tool learning agents. The paper's experiment across 18 tools found that simple few-shot prompting is often enough to trigger tool use in off-the-shelf models without additional training. However, the metrics are specific. Success was often measured by whether the API executed without an error, which is different from verifying the accuracy of the final answer. Reliably executing complex multi-tool sequences across thousands of possible APIs remains a difficult scaling problem. In the time since this survey, native features like OpenAI's function calling and the Model Context Protocol have standardized how these tools are described and invoked. The core logic of grounding, select-then-act factorization, and extrospective recovery remains a foundational framework for constructing autonomous agents.